Hello everyone. Let's continue from the last session where we were discussing about the data path extraction capabilities of compiler. So let me just review what data path extraction means. So data path extraction means that compile ultra the line compiler is able to see what data path operators we use, and it will try to extract the maximum possible. It will try to extract the maximum possible number of operators and put them in a single module. I mean, already given that, let's say you have a module and you have coded a number of operations in there. So what DC will do is try to extract all such operators and it will try to implement them in a single data path block, so that the optimization and resource sharing is able to make the maximum use of optimization and resource sharing. So we'll see. We saw this in the last session that extraction only occurs in such cases. These are the operators that are extracted as part of the data path, and these shifters and equality comparators are not extracted. So let's see one example of RTL code, and we'll see an example of report resources where it will show what data part will be extracted. So yeah, let's look at this example now. So this module contains an input. So there is no module definition here. So these are the inputs and this is the output. There are so many. There are 5. So there are 5. In fact, 7 operations taking place. I1 is equal to A into B. I2 is equal to A into C. I3 is equal to D into F. I4 is E minus G. I5 is I1 plus I2. Z1 is I3 plus I5 plus I4. Z2 is I5 plus C. So these are 7 operations that are taking place in your RTL. Now let's see how DC will extract the data path. So you don't have to do anything special. You just analyze this RTL, elaborate, apply a constraint, and do a compile ultra. After compile ultra is done, you just do a report resources. A similar example, not exactly same, but a similar example is discussed in the lab session 4, where we see the report resources report in the lab. So now, what kind of report resources? Let's see what does it report. So it tells us that it extracted all these operations and has put them in the same module. So DC will instantiate a module comprising of designer components, and in this case, it has instantiated a single module for all these operations. On the right hand side, it is also telling what all operations are taking place. So there are 3 multiplications, 4 additions, and 1 subtraction. Let's see, it gives some code about the resources also. Let's go back to RTL and see. So there are 3 multiplications, 1 subtraction, and 4 additions, which matches the one here. So now DC, since the RTL, all the operations are in single module, and all the operations conform to the RTL coding guideline that enable us to extract this data path. So DC will just instantiate this module containing all that. Now further, it will also tell us that now it says that there are 7 inputs and 2 outputs, and it is also telling us what is the bus width. Let's go back to the RTL again. So there are 7 inputs, A, B, C, D, E, F, E, G, and there are 2 outputs. So this particular module now will correspond to data path. So A, B, C, D, F, E, G will go to these ports, I1, I2, I3 correspondingly, and Z1 and Z2 will be connected to O1 and O2 of this particular module. We are talking about this module, what DC instantiated. It tells us what are the bus widths and so on. Now let's see what else this does. So this module corresponds to this name here, the same name. Now let's see what else does it report. So now it tells us that it creates an intermediate port fan out 3 and it implements this I1 into I2 plus I1 into I2. I1, I2, I3 correspond to A, B and C. So it actually did A into B plus A into C. We can see a similar operation here. I5 is equal to I1 plus I2, A into B plus A into C. So it created an intermediate fan out 3 port with this operation. It contains 2 multiplications, 1, 2 and 1 addition. Right? Then O1 output is simply fan out 3 plus I4 into I5 plus I6 into I7. So it is able to determine that O1 is equal to some function of fan out 3. You can verify it yourself from the RTL. So O1 corresponds to Z1 and Z1 is I5 plus I3 plus I4. So you can verify that this in fact is the case, and it tells what all operations are needed. Again, O2 is equal to fan out 3 plus I2. So it is able to use one intermediate output here to compute the O1 and O2, which is the output, right? So this is all these reports here are telling us that DC is able to extract a data path. It is able to create a module, one single module that implements all of these, and how the input and output are connected. Now remember, if you do a default compile without setting the variable that controls the ungrouping of design where, you will not see this module anymore, because this will be ungrouped. All the design where will be ungrouped. So to see this module, we see an example in lab 4 also that we set this variable to false, compile ungroup DW to false, and we see that the netlist now contains the module and all the DW modules. Right? This is the implementation report. Now it comes to that what kind of implementation are we doing. So it tells us that the implementation is something, module name is something, implementation is something. STR is a generic data path implementation. So it doesn't tell us a lot what kind of multipliers or what architecture is chosen as of now. So some reports will be more verbose. They will tell us what all operators are chosen, what all implementations are chosen. We saw few examples in the lab 4 also. So this is the way where DC will be able to extract the data path, and it tells us that it implemented so and so. See, now if DC would have implemented I1, I2, I3, etc. in separate modules, then given the fact that modules create an artificial boundary, it would not have been able to reuse the resources or not been able to optimize most of it. So just by the ability of creating a single module and implementing all the operations in that single module, DC has the flexibility to reuse resources, plus it has the flexibility to optimize it. Right? So it would be a very good idea to code some. In fact, the last example we did in the lab 4 has examples of data path operations. Implement simple ALU. You could use that. You could use to experiment it more and see what kind of, how does DC extract data path and the optimization. You can also in fact compare the implementation reports between compile and compile ultra, and you will see that compile ultra is doing a much more sophisticated job with it. So RTL coding guidelines. So you should code RTL such that the extraction of largest data path block is possible, because it leads to effective the best QR. You can, there's a one Solvent article about this. You have Solvent ID, you can go and read this article. Now again it's a material side compile ultra. Ultra was introduced in 2 steps. In the first step, DC gave a command called set ultra optimization. We set the variable to be true, and the compile command was as it is. We did set the variable to true, and then we run compile. It will use compile ultra. But later, in the later versions, the compile ultra command now contains all the functionality of DC ultra. So it's a full fledged solution. So you should not worry about a lot of other factors. Compile ultra does most of the job for you. So again, I'll repeat that till now in this unit 4, while we are discussing compile ultra, we've seen that in most of the cases, you as a designer don't have to do much. You just have to run compile intra, right? We saw some and if you feel that if you see that your particular goal, timing goal or area goal is not being met, then you use these advanced synthesis techniques to achieve your goals. You do some trials, but the first pass you should always use compile intra as a default and not try anything special. And I guess in 95% of the cases your goals will be met and you will be happy. Right? So now compile ultra, let's let's discuss briefly about compile ultra. How does it operate? So compile ultra by default there are two pass compile. That means inside when you run a single compile ultra, there are two levels of compile happening. It is unlike compile command. So it has timing driven high level optimization, and these things are somewhat different than the regular compile command. It does architecture exploration for arithmetic operations. It will select the best data path implementations from the design library. There is some thing related to wide fan and gate mapping to reduce levels of logic. Yes, it employs aggressive logic duplication. Then this feature is unique to compile ultra. This one where auto ungrouping of hierarchies along critical path happens. You can stop it by saying no auto ungroup. And there is a DFT flow support, that means -1, right? So these are the options that we have seen earlier. We have already discussed these. These are the variables that control the maximum block size for auto ungroup. Designware library is you can set this in synthetic library BW and your designware would be loaded. Now what happens is that there are two options, area high effort script and timing high effort script. So these should only be used if you are doing some aggressive area and timing or timing. Not you cannot do both. Not do both. If you are either worried about your larger area or your timing goals are not being met. So if you give one of these options, then DC will employ some strategies which are not visible to us, and it will try to achieve a lower area or a better time. So there are some figures available from Synopsys, like it will give about 3% timing and 7% area improvement as compared to default compiler. These are built-in flows. They are updated from release to release, and they don't require any change to your scripts. But these should be used in very specific, because again see, each of these, every time you use some special or advanced synthesis technique, it will lead to bigger runtime. So for a big design, for a full chip, you should use them with caution. Runtime is always a priority. Now a few more examples of data path optimization. This is one example which is unique to DP Ultra, is that it utilizes the resource sharing for parallel constant multiplier. So see this example now. Temp is equal to I1 plus I2, where and O1 is equal to temp into 105, O2 is equal to temp into 625. Now temp is common here. The binary code for 105 and 621 is as follows. Now it sees that temp into 760 105 can be shared. So the implementation is not two multipliers in fact, it is just one multiplier, or the multiplier is now implemented as shift operation. So temp 105 is temp shifted by 6 plus temp shifted by 5 plus temp shifted by 3 plus temp. Temp 621 again is temp 105 plus temp shifted by 9, temp shifted by 2. You should be very clear how DC is doing this. For example, each one in the binary representation represents a shift operation. So the LSB here represents the temp default 0, 1, 2, 3. This one means temp left shifted by 3. Again, this one means left shifted by 5. This one means left shifted by 6. So this is the way it converts the multiplication by constant into addition operations, and adders are much more area and timing. They are much better for area and timing compared to multipliers, right? So and furthermore, another level of optimization, what DC does is realize that temp into 105 is common to both the constants and it can use it. So temp into 621 is equal to in fact temp into 105 plus 2 shift hours. Right? So this results into better area. This is one of the special cases where DC Ultra does a very good job. Now, yeah, this is again a very important thing: library aware mapping and structuring. Now, what DC Ultra does is that the first time you run, so it will read in the library before reading in the design. So when you read the design, it will first read in the library, and it will characterize the library and create a set of matches for each function based on the library gates available in the library, right? So what it does is that it will pre-analyze the library. So when you in the lab, you must have noticed that when we do the compile Ultra for the first time, it will give a message such that it is creating an alib file. Right? Alib is the analyzed library. So you have the standard cell library as part of the target library and link library. If you use that library, it will pre-analyze it. It will analyze all the functions. It will create a table which is very similar to the one shown in the graphic. So let's say you have an operation called that is equal to AB bar C plus A bar B C D. Now it will create multiple representations of that based on the type of cells available in your standard cell library. Some of these representations would be good for area. Some of them representations would be good for timing. Please note this is not design dependent. So the library analysis will be performed before optimization, and the information is kept in a file called alib file. If we do, there are two options. We can pre-analyze this technology library file by using these variables, alib analyze libs. This is the command to analyze library. You can do it explicitly, and alib file is generated and kept in this. When the pre-generated alib is not filed, we automatically generate alib during compiling. So we have seen this second example, this last point we have seen in the lab. When you start a lab afresh in a fresh directory, it will say that alib it is generating alib file, and the first compiler Ultra will actually take some time. It will take 5-7 minutes to analyze the particular library. So again, two options: you can pre-analyze and keep the alib file, or you can let compile Ultra analyze the library file the first time. Second time, when it finds alib, it will not do the process again. So again, what compile Ultra has enhanced constant register removal. Now, usually, so enhanced constant registers are detected by initial state simulation. So usually, let's say the data pin of a clock is tied to 0. So DC will remove that clock by default because that register is not, there's no other functionality of this register apart from the constant 0. So it will remove that register and save on it. Now, supposedly there are two registers like this, where the reset state, so on reset the second register's Q will be 0, the 0 will feed into AND gate here, and the D of first register will be 0, and these couple of registers will never come out of the reset. This is because this Q is fed back in. Now in compile or in earlier versions of DC, this type of structure was not recognized. Only single register was recognized for constant register removal. But now DC Ultra does a better job of it, and it recognizes such structure where even a shift register, unknowingly or knowingly, if it is tied like this and it cannot come out of reset, DC will remove it and replace it by ground. Obviously, this is aggressive. You should take the RTL. So many lot of registers are getting removed. So it exploits design structural characteristics such as dependencies between registers to do aggressive area. We saw that in the labs we are doing by default we are doing compile Ultra minus smooth sequential output inversion. So DC in fact does compile Ultra does sequential output inversion by default. It does one more thing is that if let's say your library does not have an asynchronous set cell and you are using it in the RTL, asynchronous set and reset functionalities cannot be implemented using combination logic, right? So if you have an asynchronous reset clock but not asynchronous set clock, it can implement the asynchronous set clock by adding inverters to data and queue, and it can use the asynchronous reset clock, or it will add the inverter to D and use the queue and bill. So again, it has some better functionalities related to logic understanding and analyzing logic. So by default, we did low sequential output inversion. It is on by default. It is disabled with this option, and it is not affected by this variable. Compile, on the other hand, is affected by this variable, right? So now it creates a sequential output inversion. What happens is that the output of clock might be inverted to provide a better optimization, but this might create problems in formality. We'll have a couple of lectures on formality. We'll see what it means and how will it create a problem. So whenever you do such thing, whenever you implement this sequential output inversion, it will give a warning or information that sequential output inversion is enabled and SVF file must be used for formal verification. So you can choose not to do this by using -1 critical output. Now let's start let's see the concept of register retiming. What is register retiming? How does it work? What are the pitfalls? When should it be used? And so on, right? Register retiming is one of the more advanced form of synthesis, where the registers or the flops are either duplicated or merged or moved around the combination block to reduce area or to make performance better. Now there are 4 kinds of register retiming operations. The first one is register moving. See the first graphic. So in all the 4 graphics, there is a left hand side and a right hand side. Left hand side is the before, right hand side is the after. So register moving involves, so register that was before an inverter can be moved as the output of the inverter in case of register moving. In case of splitting, the register at the output of a gate can be moved to the input of the gate, but now it has to be duplicated. It has to be present at both the inputs or all the inputs if there are more than 2 inputs. In case of merging, it happens the other way around. The registers at the input are removed and the register is placed at the output. So the splitting will involve an increased area because now the flop is moved. Earlier there was 1 flop, now there are 2 flops. In case of merging, reduced area. Earlier there were 2 flops, now there is 1 flop. In case of hybrid, what might happen is that the 3 registers, let's say for example here, this is again an adder, a full adder. Now for a full adder case, the register at the input can be moved to the output to save on area, right? By default, register retiming is off in the time compiler. So you have to explicitly tell the time compiler to retime. Now please note that the functionality, end-to-end functionality of the circuit is not changing. There are only 2 parameters here, area and timing. Either it results into a lower area or better timing. Now if you are confused about why the functionality is not changed, please note that pipelining or placing of registers just corrects the sequencing of events and not the logic level of events, right? So for example, in case of this full adder, earlier the inputs were registered, now the outputs are registered. It does not change the functionality of S and CO. The functionality of S and CO remains same. However, it changes the timing characteristics. Now earlier the timing check was done here at the input of this. Now the timing check will be done here. So we'll see a few more examples to make the concept clear. So the idea is, the question is whether do we want to pipeline or not to pipeline. Let's see one example of this code. The left code is VHDL, right code is Verilog, right side code is Verilog. We'll see the Verilog code. Now let's say you have a product AB is equal to A into B, product CD is equal to C into D, difference EF is E minus F, P21 is prod AB plus prod CD, so A into B plus C into D, P2 underscore 2 is DTF, Y is equal to P21 plus P22. Please note, although this is coded in single always block, each such construct, each non-blocking construct means one level of flip-flops. So what happens when it gets implemented? A into B, this is the multiplier, C into D, E into F. These are the first level of operations. So start with the right hand side, A into B, C into D, E into F. They go into prod AB, prod CD and DTF. So the outputs, so A into B, operation takes place first, then goes into prod AB. Prod AB is a clock. This is prod AB. This is prod CD. This is DTF. Now prod AB, prod CD are added and go to P21. DTF goes to P22. DTF goes to P22 directly. Y is equal to P21 plus P22. There is an adder here. P21 plus P22. Through a flop, it goes to Y. What are the registers in the design? Prod AB reg, prod CD reg, DTF reg, P21 reg, P22 reg, Y reg. Right. So this is the only way you can code. You have as a designer, the designer has implemented pipelining in this code by the way of RTL coding. Right. Now let's see what happens to the timing. Right. Now here, these multiplications of the operations are bigger in area and they are slower compared to this adder. So the critical path will be from A to this block, A to this block, B to this block, C to this block, D to this block. So these are the pass-through multipliers. These paths are critical paths as compared to this, right? So design violates timing, right? Let's take some figures. Let's take the clock period to be 10 nanoseconds, clock to Q delay to be 1 nanosecond, clock to Q delay of the clock, setup time of the clock to be 1 nanosecond. Now, let's say the adder takes about 4. The adder takes so this total multiplier here takes 16.5 multiplier delay. The violation would be 7.5. 16. So the time available to you is clock period is 10 nanosecond, clock to Q delay is 1 nanosecond, setup time is 1 nanosecond. For the path A to flop, this path here, it will be multiplier delay plus the setup time should be less than the clock period. Assume the input delay to be 0 here. So let's say the multiplier delay is 16.5, clock period is 10, 16.5 plus 1 clock to the setup time, the data should be arriving 1 nanosecond before the capture clock is. So 1 nanosecond gets added to the data part delay. 16.5 plus 1 is 17.5 minus the clock period is 10 nanoseconds. That is the flag. Since the data arrival time is later than the data required time is 10 nanoseconds, data arrival time is 16.5 plus 1, 17 point, flag is minus 7.5. But let's talk about this part now. Now let's say the adder delay is 4.2, clock to Q delay of this is 1 nanosecond, so it's 1 plus 4.2, it's 5.2. It should arrive 1 nanosecond plus prior to the capture edge at 10. So 5.2 plus 1, 6.2. So total data part delay is 6.2. Required time is 10 nanosecond. If subtracted, slack will be positive 3.8. Similarly, you could do the exercise for this. If this adder takes 4.3, the slack will be 3.7. Please make sure that you understand these calculations. Better take a pen and paper and do the calculations yourself. The important thing here is that the multiplier here is slow and there is a violation. Adders here are comparatively faster and the timing is meeting by a good amount. right? Now consider these pipelining, these blocks are just to facilitate sequence of data, right? Consider the complete path, this complete path. We see that the slack is 3.8 is available here, 3.7 is available here, and violation is minus 7.5. If I add 3.8 plus 3.7, the sum is 7.5. Ideally, end-to-end path should be tiny because the total slack negative 7.5 plus 3.8 plus 3.7 is 0. So ideally, is there a way now to use this? This is called time borrowing, right? This is I want to borrow the time here to there or this time to here. Both of these positive slacks, I want to borrow it and meet this solution. Now, only when in a pipeline design, I'm sure that you would be reading about pipeline design in a greater course also. In pipeline design, the complete path, the design has the best performance whenever each combinational cloud is of similar delay. In such a case where one combinational cloud like this one, like this cloud here, has much more delay than these combinational clouds, you are limited by the performance of this combinational cloud. Now in this case, if you don't do anything special, your frequency would be the lowest frequency at which you can work would be minus 7.5 plus 10, 17. So you get a lower performance. However, if all these clouds were of similar delay, then your frequency will be maximum. In this case, your frequency can still be 10, your time period can still be 10 nanoseconds, given that if you are able to borrow this time. So what do we do now? We borrow slack from another stage. How do we do that? Pipeline runs fastest when logic is equally balanced. Leftover positive slack can be used to reduce area. The question is, can we code our HDL to achieve this balance? Answer is no. We cannot code our HDL. Why? Because this is the only way we can code our HDL. We do not know or want to know the functionality of this multiplier. We are not implementing this multiplier by structure. We are just using a multiplication sign. We can only place flops at the logical boundaries, like done here. We cannot place flops in the middle of the multiplier because we do not here there is no structure of multiplier in place in RTL. So the answer is we cannot code our HDL to achieve the balance. This can only be done after the implement. I mean, at the second level of the implementation, right? So to achieve this balance, first of all, some structure of multiplier should be available to us. And when the structure is available, the structure is available only after the first pass of compile, right? So what happens after we distribute the slack? So after we distribute the slack, we move 3.8 to here, we move 3.7 to here, the slack here becomes 0, the delay here becomes 9, the delay here becomes 8, the delay here becomes 8, right? You can do the calculation on paper to confirm that these are correct. Ideally the slacks is since the sum of positive slacks here equals the negative slack here, after distribution the slack should be 0 at all the places, and the combinational cloud here they are balanced equally. Here the delay is 8, here the delay is 8, here the delay is 9, yet I say they are equally balanced. Why? Because in the stage 2 and 3 there are additional clock stage. So clock to Q1 and clock to Q1 is here, but here we are assuming the data comes at 0, not after. There is no clock here, right? We are assuming the data comes at 0. In this stage 2 and stage 3 the data is coming at 1, right? So please make sure that you understand this, draw the waveforms on paper and see that you can. So this is if you understand this calculation, you will understand the report time. So I would say go the other way around. Go through the lab, make sure that you understand the report timing report, and then you can do the calculation on paper for this circuit, right? Now, there are a lot of instances like this, and now we know that we cannot code our SDL to achieve this kind of balance. it is not possible since we are using simply the multiplication operator, not the complete multiplier. So what is the way out? Way out is register retiming by DC, and so it's a technique to optimize the gate level netlist for timing in possibly register area. Majorly it is for timing, right? It is used to pipeline a gate level netlist that can be used for better throughput. Now there are two ways by which we could do register retiming. One is compile ultra minus retiming. So the algorithm used by compile ultra is for adaptive retiming during optimization to improve delay. Second is called optimize registers or set optimize registers. Now this is a very extensive retiming. So compile ultra retiming is kind of a basic retiming. It is used for general logic. Optimize register is something that is used for very special cases of complex data types. Again, recommendation is to use this first, and if you are not able to meet timing, then go to optimize register. So what optimize registers does? Optimize registers does lot of things. It does register moving, moves registers across combination elements like we saw in the graphic earlier. It does not modify any combination element. Does minimum period retiming regardless of area. Does minimum area retiming following minimum. So first, it will minimum period means that it should meet the clock frequency that we apply. Then in the second phase, it can also do some area optimization. In phase 1, this is phase 1. Phase 2, it has an incremental compile boundary optimization, combination optimization, optimizes combination element between registers. Anyway, the compile command will also do. Does not move any. So first phase, it will do register moving to achieve better timing. In second phase, it will optimize the combination area between these sequential elements. This will optimize the area and timing both. Right? Formality support, very important. But now you are moving registers. We will talk about in formality. Whenever we move registers, so RTL, the placement of the sequential elements is now altered in the netlist. The sequential elements that are in RTL are not at the same place in the netlist. They are moved around. And formality considers all sequential elements as compared on. That means we will see that in formality in much more detail, but it's a problem of formality. So there should be a way by which we tell formality or the formal setting tool that my registers have moved. So DC design compiler provides such kind of support where you can tell formality in a file called SCF that my registers have moved. So this is an example. So existing circuit or clock period is 10 nanoseconds. One side is violating, it's 10.2, other side is 7.5. So now it will move. Circuit after BRT means again BRT is different for I think register timing, something like that. It will optimize register area. So here it did some optimization to both. It optimized register area. I'm not sure what is the circuit here, so we cannot tell with 100% surety what happened here, but seems it decreased the signals that are passing the boundary, and it did it did the slack improvement also by borrowing slack from this stage to this stage. So the command is optimize registers minus Q give the period. Primary goal is obviously timing, secondary goal is area. It preserves functionality at our IO boundaries, which is very important. Of your design, the functionality of your codes does not change, which is very important. It operates at the gate level. Register placement is not restricted by RTA operator boundaries. So you code your RTA the way you like, obviously following guidelines, and let optimize registers do the rest of the job. Now, compile ultra now has most of the, so there is a command called set optimize registers. Synopsis tells us that it now has most of the options for optimize registers. So optimize registers is a very expensive command. It has lots of options to control optimize registers. You can read the man page of it. You can see the help option. So, but ideally, what you should do is that at first pass you should try the set optimize registers command. It contains most of the functionality of optimize registers, How do you do it? You say set optimized register with some options, whatever is available or whatever you want to use. You tell what are designs you want to do. So this is where you tell what are designs you want to do the optimization on, and then do a compiler. So compiler will look for the designs on which you have set this optimized register, and then it will try to retime only that part of the design. So you could use it selectively on some part of the design. Right? Now users can trade off between QR and runtime for reset state justification during retiming. So there is a functionality related to reset state. So what you could do is that there is one option called justification effort, through which you could control what kind of retiming, what time, how much time does DC spend in retiming. Now, again, I'm stressing the point that all such steps will increase the runtime a lot. So if your register retiming is enabled, then your runtime will be much more compared to the default compiler track. The option justification effort kind of controls that. So if you say low, then DC will finish quickly at the cost of obviously the quality will not be that great. You could use median, which is default. It has the best trade-off of the QR and runtime. If you set to high again, it has potentially longer runtime compared to the low and medium, right? So again, optimized register also supports register retiming on subdesigns. No need to change the current design. You just set optimized register to true and set the design names and do the optimized register and say only attribute the design. So these kind of commands, let's say set optimized register, set don't touch, set don't use. These kind of commands, the set commands, they will place some attributes on the design. For example, if I say set optimized register is true and the design name, let's say design name is X. So that design X is marked by an attribute called optimized register true. These kind of these things are called attributes like optimized register, don't use, don't touch. So all these are collectively called attributes, and these tell DC. So let's say the library cell. If I set some library cell as don't use, it means that I'm telling DC that this cell is attributed as don't use. So DC will look at attributes and decide whether I want to use this cell, whether I have to optimize this, or whether I have to retime the design, and so on. These attributes are very powerful feature of design compiler and of runtime, and you could build. So DC uses them internally, and as a user we can also use them. For example, I want to find out the list of all the library cells that are don't use. So what I could do, I can write a for loop in Tcl, which will go through all the library cells and it will get the attribute of the library cells. The attribute name is don't use, and I will check that whether don't use is set to true or false. So I can write such programs, such powerful programs in design compiler or runtime or any Tcl based interface just by getting the value of attributes. So there's a list of attributes which are available. Now these attributes are again designed, again object dependent. There are some attributes which are special for design. There are some attributes that are special for cell. There are some attributes which are very particular to net. So we'll see a lot of attributes in runtime in Unit 5. We'll see some examples. But here the minus only attributed design means that do the retiming only on designs that have this attribute, optimized registers attribute set to true. So this is the meaning of attributes. I just want to clear that, right? Again, compiler has support for last retiming. So we saw these when we discussed about retiming. This was the flop retiming. All these cases were of flip-flop retiming, where the flip-flop is moved from one place to other, or either duplicated or merged or whatever. But DC Ultra also supports compiler also supports latch retiming. So, in case of latch retiming, similar to clock retiming, the time borrowing happens. The important thing is that the latch phase, if you are using a single clock, the latch phase should be inverted. So there will be two clocks, so there are latches, and you want to share, you want to borrow time from one to other, one combination cloud to other combination cloud. Now in this case, the middle latch should have the opposite polarity when compared to this latch and this latch. Only then the time can be borrowed. Why? Because latch as opposed to flip flop is level triggered, and it's level triggered. During one phase of the clock it is transparent, and whenever this launches data, this will launch data on the closing edge. On the closing edge, so whenever this closes, this should be transparent. So that so what happens when these two are of different polarities is that this latch behaves as a combination element. So I'll see if there is a So in case there are two different clocks, they should have alternate phases. If there is same clock, then they should have different opposite polarity. So let me now let's say this cloud here is has burst timing. I'll put a cross here. This cloud has burst timing when compared to this cloud. Let's say this cloud here is the one from which I want to borrow. This is a cloud with the burst timing compared to this one. But the first question we should ask is that, let's say the period is 10 nanosecond. This cloud here takes, let's say 6 ns, and this cloud number 1 takes 6 ns, cloud number 2 let's say takes 4 nanoseconds. Now first question we should ask whether the sum of these two clouds is less than the clock frequency. In this case, let's say I want to meet for the time period of 10 nanoseconds. I find that okay, yes, 6 plus 4 is 10, it's barely meeting. Now what I can do is, by adding a latch here of an opposite polarity, what I am trying to do, I am making this whole circuit a one single combination block. Why? When this will launch data, the data will come here at 4, after 4 of the closing edge. At that time, if this latch is open, data will shoot through like a combination block. A latch during the transparent phase is like a combination block, it's like a buffer. So this data will go through here, and at the capture edge, the data will be available after the sum of delays of cloud 1 and cloud 2. Assuming the buffer delay, the latch delay in transparent phase is close to negligible, assume that for this exercise, we see that the data at this point arrives after the delay of cloud 1 and cloud 2. So in effect, the latch here is transparent, and we say that the timing, it was able to borrow timing from 2 to 1 or from 1 to 2 as the case may be. So this way, design compiler optimized registers has the retiming support for well. So see, the idea is well-formed symmetric two-phase system of latches. This is called two-phase system of latches. Ideally, your RTL will not have this. It is not recommended to design with latches. They are very used in very special cases, some very special circuits. So just keep this in mind that the support is available, and in most of the cases you will not encounter this. But we will see timing reports. So now this is, we are discussing synthesis. In unit 5, static timing analysis, we will assume that a netlist is available to and design is available to us, and how do we time that design properly. So in such cases where the latches are already present in the design, you know nothing about it, you have to make sure that you correctly check the timing. And in such cases, we will see that how the timing report looks like. It's slightly bit more complex than a clock to clock report, but we will see how the time borrowing looks like. Right? So this is the way it is implemented. Again, if you have clocks if you have latches So there can be cases of a latch between two latches. There can be a case of a latch between two clocks. Right? They are both similar cases. So if you have two separate clocks, then they should have alternate phases. So see, the transparent here does not overlap with the transparent here. So whenever this launches data at the closing edge, this latch is already transparent. That is the idea of latch treatment. Right? So this ends the this session of advanced synthesis technique. Summary. First up, you should not use any of these techniques. The first rule is compile ultra should be used first with default options and the quality of result analysis. What comprises the quality of results? Quality of results means you should check the timing, you should check the area, you should check the report constraint minus all violators and make sure that your design is meeting all the goals. In case your design does not meet all the goals, you can use advanced synthesis options. First, you should check whether you are using compile or compile ultra. Use compile ultra in most of the cases. If your goals are not being met, use advanced synthesis options. And even in advanced synthesis option, don't go to retiming, don't jump to retiming. First, verify that your goals are realistic. Use some, you can use group paths, and so let's talk about timing problems. So if you encounter timing problems, first of all use group paths. See if any other group has violation or the critical path in your group is causing some other paths not to for some paths in your group, some like we saw in lab 4, some paths in the same group, some paths which are of low priority like IO path, like input and output path, can cause a register to register path to violate. So make sure that your groups are correctly created, and let's say for very critical paths, use a separate group, create a separate group so that we'll be able to focus more on that. So first, use group paths. You can use critical range also if you want to make sure that your timing is not met till flag 0, but you should have a positive flag. Use critical range for that. Each of this will increase the runtime obviously. Then come to map effort high. Map effort high means advanced critical path. Use that. Even if your design timing is not met, then again check whether your design goals are realistic. And in the last, retiming should always be the last step. Right? Now there are design components like multipliers. Right? Multipliers are big blocks. They are slow, so they most of the time they have timing problems. So you could use a pipeline multiplier from design your library. What is pipeline multiplier? Pipeline multiplier has an internal pipeline built, but that pipeline is not at a fixed location. DC will move around that pipeline based on what is your timing constraint. So it has an inbuilt retiming built into it, right? So you can use such options. You can go through designer literature and so there will be a DW mild, there will be a DW pipeline mild, and so on. Right? So, but please note that all these advanced features like retiming or mostly retiming will or sequential output inversion will cause formality issues. So you have to make sure that you are well versed with how to solve these beforehand, right? So in unit 4 further we will discuss about the power optimization. In the next session we will see what kind of, we'll see first the basics of power, what kind of power numbers are we talking about, how do we optimize power, and then we'll move on to unit 5, which is time. Thank you.